One last example for chapter 3, and this is class 12, so we're finishing up chapter 3. I found this in Cengel, and I thought, that's a fairly good question to ask, right? So we have like this piece of iron that's 80 degrees Celsius, and it's got a mass of 50 degrees, 50 kilograms. And we put it into a thing of water of 0.5 cubic meters of this 25 degree water. And we want to determine what the temperature happens when it reaches thermal equilibrium. Notably, that this is, well, it's not hairy, but it looks like hairy now. It's insulated, right? So, what we're gonna, if we're gonna write out the big equation, energy equation here, in a process, take a look at that, and it's insulated, so it's adiabatic, meaning no heat can transfer across this boundary, and it's going to be the same volume. So constant volume means no work can be done. So therefore, this should be U2 minus U1. Why did I write that wrong? I don't know. I can't say that I'm tired. I had a good night's sleep. Anyway, they must be equal. So they're going to be equal to each other. Before has to equal after. So what you could really say is that you could say what the change is, right? So the change is going to be 0. So the change in each of them is, when added together, you could say the change in the iron plus the change in the water is going to be equal to 0. That's a safe statement, right? That's really no different than saying this. It's just saying that, like, okay, here's all the entropy in the difference between these two, and the difference between these two, they're going to be equal to 0. So they're going to not entropy, internal energy. My bad. I'm sorry. So what we could say is we have the mass of the iron times the specific heat of the iron times the temperature that at the end, which is going to be T2, that's going to be the temperature, both are going to have the same temperature, minus the iron temperature at state 1, plus m of the water, mass of the water, the C of the water. We could say that C. Actually, I think for liquids we just have 1. We usually say CP, because the volume doesn't change. Minus T water 1 equals 0, right? So we haven't done a problem exactly like this, but it seems to be a thermodynamic heat transfer kind of problem that's dealing with specific heats that's worth looking into. So we could, well, first off, we need to go up to, let's go write down this stuff so we can communicate how we did it. Let's go to table, and we don't know quite yet which table. See, I might end up with a different value than I got, because I just copied it out of the book last night because I was tired. I didn't have the book in front of me. That's no excuse to be lazy, but it is a reason, right? Boom. And here is iron somewhere in here. Where'd you go, iron? Oh, it's in the metals, that's why. We have 0.42 is our specific heat. We're calling it CP. And then for water, we did this a minute ago. 4.18 is our specific heat. So this is table A3, table A4. Table A.3, we have C of iron is equal to let's get a different value. You son of a gun. I'm done, like a short attention span's working again. 0.42. And there's, what are these, kilojoules per kilogram degree Rankine? Sure. And then we have C of water. I was just thinking about something a minute ago. I did something kind of naughty the other minute ago. I said ranking. Oh boy, wow. I should not teach you anything today. Unfortunately, I'm not. This was 4.18, but I just used that a minute ago with degrees in the previous example, and I can't do that because this thing is a kilojoule per kilogram degree Kelvin, so I should not be multiple. I did though. I multiplied it, but I shouldn't be. I knew better. I knew better than to do that. I bet people will comment on that video. Do you think people will? Let's see if they do. Well, go make a comment on it so you can feel smarter than me. Shouldn't be very difficult. So right here, 0.42. I'm going to have to recalculate this because on my page, I have 0.45 because that's what it said in the other books table for this thing. So you just pick any damn thing you want. It's really just do anything you want. It doesn't really matter, does it? So we had. Ooh, wait. I don't know the mass of the water. What I needed to do was look up. I had to go find. It's gonna be close enough. Want to go close enough? Okay. The mass of the water is going to be equal to the volume of the water that we're told divided by the specific volume of the water. And this is actually usually most sane people say that it's the density is 1,000 kilograms per cubic meter. Our book, other books get like all crazy about this, but anyway, so this is supposed to be 0.5 cubic meters. And this, if it's the inverse of the density, which is 1,000, you need a 0.001. It's close. It's very close. So I get 500 kilograms. So that's why I started writing 500 up in here. So that's where that 500 mass of the water and 4.18. And then T2 minus, I'm going to have to do careful math here live. Oh, that's going to be scary. Well, when I'm scared, what I usually try to do is go simple here. Let's see. I go 50 times 0.45, boom. And we're going to get 22.5. Which makes sense, T2 minus, that's going to be good, times 80, boom, and I get 1,800. It's going to be plus, 500 times 4.18, boom, and that's going to be 2,000, is that right? Yeah, I guess, yeah, it makes sense. 2,000, no it doesn't. Oh no, okay, it does. 2,000, so right there was critical thinking, what I just did. You heard me arguing with myself. I know, it's not. It's not pleasant to hear someone argue with themselves, especially if you're walking down the streets of Manhattan. All right. And so those two are going to jump over to the other side. So we're going to add those together. Of course, this thing's dominating right here. And then we're going to divide by 2,090 plus 22.5 and divide. And all we're going to get for T2 is 25.59 degrees Celsius as an answer. And you think about that, now the water has only gone up 0.59. Well, that's because there's so much of it, 500 compared to 50, but also its specific heat is so very large compared to this right here. So it doesn't really raise the water temperature very much. It'd be interesting if we did this with something that was much, much higher, much, 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 much hotter, right? Like you see all those videos where they're taking this big, I don't even know what it is, a steel ball or something, and they dunk it into things and watch as it burns through. Don't know why that's interesting, but I've clicked on that stupid Reels video thing a couple times. So this is the last example. I'm not sure if it was worth it. Sure, it's something that you'd want to try to find out. We'll see you in class 13 where we start chapter 4. So long.